Hello, welcome to the class of Advanced Stats and Econometrics. So, in today's lecture, we are going to discuss multivariate analysis. And the learning objectives of this chapter is uh, explain what multivariate analysis is and when its application is appropriate. Define and discuss the specific techniques included in multivariate analysis. Determine which multivariate technique is appropriate for a specific research problem. Discuss the nature of measurement scales and their relationship to multivariate techniques. Describe the conceptual and statistical issues inherent in multivariate analysis. So, what is multivariate analysis? All the statistical methods that simultaneously analyze multiple measurement on each individual or object under investigation, and why we need to use it for measurement, for explanation and prediction, and for hypothesis testing. Basic concepts of multivariate analysis. First is variate, second is measurement scale. So you have two different types. One is non-metric, other is metric. Third is multivariate measurement, measurement error, and types of techniques. So what is variate? So variate is a linear combination of variable with empirically determined weights. Weights are determined to best achieve the objective of the specific multivariate techniques. So variate equation, say y transpose is equal to w1 times x1 plus w2 times x2 plus w3 times x3 till wn times xn. So each respondent has a variate value y transpose. The y transpose value is a linear combination of the entire set of the variables. It is the dependent variable. Potential independent variables, for example, is x1 can be income, x2 can be education, x3 can be sample size, and so on. So type of data and measurement scales. So there are two types of data. One is non-metric or qualitative, other is metric or quantitative. So for the qualitative or non-metric, we have nominal scale and ordinal scale. Nominal scale is only for identification. You cannot compare. Ordinal scale you can compare, but you cannot say by how much one is better or one is worse. The only thing you can say is one is better for ordinal scale. Metric are interval scales and ratio scale. Interval scale, so equal interval signifies same magnitude, and for the ratio scale you have meaningful zero, means absence of the phenomena. So temperature measured on say centigrade or Fahrenheit scales are interval scales. 0 degree does not mean uh, no heat, whereas temperature measured on Kelvin scale is ratio scale, because 0 degree Kelvin means no heat. So nominal is size of the number is not related to the amount of the characteristic being measured. Ordinal larger number indicates more of the characteristic measured, but not how much more or less. And interval, for metric we have interval and ratio. Interval contains ordinal properties, and in addition there are equal difference between scale points. Ratio contains interval scale properties, and in addition there is a natural 0 point. The level of measurement is critical in determining the appropriate multivariate techniques to use. Measurement error. All variables have some error. What are the sources of error? Measurement error distort observed relationship and makes multivariate techniques less powerful. Researchers use summated scale, for which several variables are summed or averaged together to form a composite representation of a concept. So in addressing measurement error, researchers evaluate two important characteristics of measurement. First is validity, the degree to which a measurement accurately represents what it is supposed to. Second is reliability, the degree to which the observed variable measures the true value and thus error free. So these are the two important concepts related to measurement errors: validity and reliability. Statistical insignificance and power. Type 1 error or alpha is the probability of rejecting the null hypothesis when it is true. Type 2 error or beta is the probability of failing to reject the null hypothesis when it is false. Power of the test or 1 minus beta is the probability of rejecting the null hypothesis when it is false. So we have four possibilities. When the null hypothesis is true, either we can fail to reject it, that is a correct judgment, so that is 1 minus alpha, and the remaining is alpha, which is type 1 error, error in the sense that hypothesis was true and it was rejected. If null hypothesis is false and you fail to reject it, then it is beta, it is type 2 error. But if you reject a null hypothesis, that is 1 minus beta, that is power of the test. Power is determined by three factors: effect size, the actual magnitude of the effect of the interest, the difference between mean or the correlation between variables. These are the examples of effect size. And alpha is set at smaller levels, power as it is set at smaller level, the power will decrease. So typically alpha is 0.05. Sample size is important. As sample size increases, power increases. So with very large sample size, even very small effects can be statistically significant. Raising the issue of practical significance versus statistical significance. So here we can see in table power level for the comparison of two means, variations by sample size, significance level and effect size. When alpha is 0.05, that is 5%, and when alpha is 0.01, that is 1%. Effect size can be small or moderate, say 0.095 and 0.338. So this is for that the sample size should be 20. If you have sample size like 40 and alpha is 0.05, you will see that as sample size increases, then the effect size also increases in all the columns. If you watch this, that alpha for one, when it is set at 1%, then compare it with when it is set at 5%. When it is set at 1%, you see the power decreases. If you decrease the alpha, the power decreases. If alpha is 5%, power was 0.095, and when it is 1%, it is 0.025. And it also depends upon the effect size. If effect size is small, say 0.2, or if it is moderate, 0.5. So if it is moderate, then what will happen? This will also decrease. So if it is smaller, then the effect size is smaller, then the power will be less. If its effect size is moderate, then power increases, so it is taking large values. So we can see that power level is related with the sample size, alpha and effect size. So impact of sample size on power, we can see that effect size is 0.35, suggested power 0.80, and power is plotted on y-axis and sample size per group is plotted on x-axis. As sample size increases, power increases. But if you decrease alpha from 0.10, that is 10%, to 5%, alpha is 0.05, then the power decreases. Similarly, if you decrease it to 1%, alpha is set at 0.01, it all further decreases. So we can say that power depends on the sample size. As sample size increases, power increases. As alpha decreases, then power also decreases. If you increase alpha, then the power will also increase. Statistical power analysis. Researchers should always design the study to achieve a power level of 0.80 at the desired significance level. More stringent significance level, say 0.01 instead of 0.05, requires larger samples to achieve the desired power level. Conversely, power can be increased by choosing a less stringent alpha level. So you can increase power by increasing alpha. So if it is 5%, you can increase it to 10%. Smaller effect size always requires larger sample sizes to achieve desired power. We have already seen that smaller effect size requires larger sample size to achieve the given level of power. Any increase in power is most likely achieved by increased sample size. And the reference for all this is book Multivariate Data Analysis, 8th edition, Engage Learning, and authors are here Babin, Anderson, and Black.